So, let's get started. Okay, let's get started. First of all, I didn't know that the class was dieting, so I'm going to be dying with all this stuff. So please help yourself with that's where it was. Okay, then. Okay. So Daniel Kahneman. How many of have I mentioned Daniel Kahneman? Okay. So Daniel Kahneman and his very good friend Amos Tversky have done some of the greatest work in behavioral economics, in particular showing that people are irrational, that we are predictably irrational. All sorts of crazy things we do, and so it's kind of strange that we try to actually develop AI agents that are perfectly rational, when in fact we are completely irrational ourselves. And there are several things that are irrational that we do. In particular, for example, you may have noticed here, I put this thing up, that we are somehow not influenced by statistics as much as by individual visceral images. How many of you have seen Schindler's List? Do you remember that Steven Spielberg makes this one little girl in pink because millions of people being gassed in gas chambers somehow doesn't hurt us. We are affected by one person. Okay, it's not something to be proud of, honestly. In fact, people have said that a single death is a tragedy, a million deaths is just a statistic. And that's not something to be proud of, because in fact we should be affected by statistics, but we are somewhat irrational. In fact, Oscar Wilde actually said that it's a mark of a truly educated man to be deeply moved by statistics. So the stuff that you skip to look at the pictures, that is you showing that you are irrational just the way you were born. But one of the other kinds of irrationalities that we have, that Kahneman actually showed, is this thing called peak end rule. So suppose you are having a very bad surgery of some kind, what he basically tried to show is that people remember that surgery experience not by the entire surgery, but what just happens towards the end. In particular, he did this interesting experiment. I don't know how he got away doing that experiment, but for some people having this surgery, towards the end, they increased the pain a little bit more. And others, they just tapered it off. They had the same exact surgery. And the people who had the slightly higher pain towards the end thought it was a really bad surgery. And you should never have that surgery again. And people who had the tapering effect, they thought, oh, that's fine. Okay, so that's called the peak end rule. And since you are also irrational, I'm trying it out on you. I'm giving you raspberry bars just so that you'll remember only sweet things about this class. Right? And then you will forget all the other sweet things that might have happened. But, so that's my best attempt at trying to use your irrationality against you. But anyway, seriously, as I said, part of being educated is being aware of the fact that we have these irrationalities and trying behind our back, trying to work on our own irrationalities. Okay? Do try to be influenced by statistics. Don't just wait for the girl in the pink to show up for you to understand that Holocaust was an amazingly bad thing. Okay? You should not depend on just visceral single things, even though that's how we have evolved to be. Okay, so that's about that. And during the class time, actually maybe I'll just put this to the side in case anybody wants to eat during the class. Please come by. I'm a little worried that I'm not instructed too many of these. So any of you need to eat during the class time, just come here and help yourself. Yeah. I don't know that there is a chair. Yeah. So that way you don't have to feel worried about. I think just put that one side here. Unless you have the chair there or something. Okay. Yeah, that's fine. Yeah. Okay, so by the way, some of you already probably noticed, and some, in case you didn't, there is a mandatory assignment that you have to complete by 12:3. This essentially asks you to sort of do some sort of a reflection on what happened in the class. And then you post it on Piazza. I believe some people have already started posting. I want you to do it by 3rd, just so that I will be able to see if there is any patterns and talk about them on the last class, which is 5th. The next week are the 2 last classes for this. Again, just to remind you, this is essentially about the course content. It has nothing to do with the course delivery. And the instructor, please do not use this to say either good or bad things about me. Don't feel compelled to do any of that. You actually have a separate avenue for anonymously saying, as part of the college evaluations, college teaching evaluations, all the things that you wanted to get. I'm told there are about 20 people who already responded. I can't see the responses right now. They don't let us somehow see it until the grades are given. I don't know why. So, given that the grades can be changed afterwards, I don't know why. But anyway. So please do take part in that to give anonymous feedback about the class. But this is mandatory. This is actually 10% of your final exam. Okay. Then make sure that you do. Okay. So any questions before we go forward? Okay. So last class we were talking about factor algebra. 2 things. First of all, there is going to be a mini project that's going to be released, hopefully today. This one has no coding involved. It is for you to actually play with Bayes networks. You specify the Bayes networks. In fact, it's it's Christmas in Springfield and in Simpsons, and then you will try to help write some the right kind of Bayes networks to stop the nuclear catastrophe that's ever going to happen there. Okay, so that's basically what you're going to do for that. That's again, there's no coding involved, but you try to exercise what you learned about the Bayes networks here. Okay, and we're trying to make sure that it would be auto-gradable, so that's why it might take some time. I'm most likely going to release the project, but then pending the exact details on how to submit it. Currently it says hard copy, but most likely we'll try to make it in such a way that the team don't have to deal with big amount of hard copy. Okay, so that's going to happen. That's going to be due the last class, which is basically called 5, which is December 5th. Okay, so any questions? Okay. So we were talking about factor algebra in, I believe, last class in the extended session, I believe. And that's very important to understand. I hope you all looked at what has happened there. And you understand that essentially the conditional probability tables can be thought of as factors when multiplied will give you the joint distribution, where the multiplication is not a matrix multiplication, but it is this funny join multiplication. So you sort of join the 2 relations and you multiply the numbers. That's what we have done. Okay. And so anytime I talk about, in general, it's not surprising because in the very best case, probabilities multiply, right? That's what you have seen. Whenever, if you are, if I ask you what's the probability of A and B and C being true together, you don't know how to answer that. But if I say they're all independent, then you say, wow, it's probability of A times probability of B times probability of C. Okay, so in the best case, essentially probabilities multiply. Okay, and what we are essentially trying to do is, it's not necessary that everything is completely independent of each other, but instead they have some dependencies, but the dependencies are fewer than the worst case scenario, and so in which case, what you're multiplying is these conditional probability tables. Okay, so this will work, as I said last time, also for completely independent scenario, where there won't be any, in this on A, B, C, there won't be any edges at all between A and B and C. Okay, so that's about factor algebra, and you have to keep that in mind, and you, in fact, think of graphical models essentially as a way of providing the topology of the model, which is the connections between the variables, that will tell you how they factorize. And then the actual numbers are the conditional probability in the tables. You see what I'm saying? So it's like the most important part really of the Bayes network is its topology. And then of course the numbers. Okay, once you give the topology, you already know what conditional probability tables you have to provide, and then you multiply those tables, you'll get the full joint. Okay, so that's the thing that you have to understand. And really there's nothing more to Bayes networks essentially, or graphical models, than factorizing a huge joint distribution into smaller pieces. That can be one. That's what it is. Okay, now since I kept saying this, so one of the things that they're actually trying to do here is, in essence, there is a conditional independences that are being given. So if in the very best case, if A and B and C is the variables, in the very best case in terms of needing the least number of numbers, they'll all be independent. In which case there won't be any edges at all in the network. In the very worst case, it will be a complete acyclic graph. In between there will be some number of edges, but some number of edges are missing. So in essence, what we are trying to do in providing this topology is to say, it's not all or nothing. It's not either fully independent, everything is independent of everything, versus everything is dependent on everything. Depending on the domain, some things are correlated with some things. Okay, and you're sort of trying to provide what are actually the minimal ways of how those things are correlated. And once you provide that, to some extent, the edges in the Bayes network provide you conditional independence assertions. And given certain conditional independence assertions hold, you can then derive other conditional independence assertions. And why are the conditional independence assertions useful? They're really only useful in devising the inference algorithms for Bayes networks. You see what I'm saying? Why is the independence, if in the best case everything is independent of everything else? What has that saved you? Essentially it saved you, you can compute any probability very fast by essentially using the fact that everything is independent of everything. Plus of course you can start with fewer numbers. Okay, so conditional independence assertions are used in the algorithms in the inference algorithms in trying to do the Bayes network inference faster. Okay, keep that in mind. So the question, of course, then is, can we say a little more about conditional independences? So in general, you try to write conditional independence assertions this way. So X is conditionally independent of Y given Z. In general, X, Y, and Z, they can all be sets of random variables. They don't have to be independent random variables. They don't have to be individual random variables, not single random variables. They can be sets of random variables. So the set X of random variables is conditionally independent of the set Y of random variables, given the status of the set Z of random variables. Status means what are their values. In general, that's the kind of, given this evidence that those two are independent. Okay. Now, once I know this, if for example x is independent of y given z, it can be used in many different ways. For example, these are all possible ways of using that one single assertion. If x is independent of y given z, then if I ever ask you what's p x and y given z, you get to write it as px given z times py given z. You see what I'm saying? X and y. So the difference is if z is not there, if I just write this, x is independent of y, that means it's just independent of y. You don't need to tell any other variables. But if x is independent of y given z, which is the more general condition, then only when you know the value of z is x independent of y. Okay? And in general, so then in that particular case, so if this is true, then you can use this in x and y given z is x given z times y given z. Similarly, p of x given y and z. Okay? Two pieces of evidence, y and z, is really nothing but p given p of x given z. Because y doesn't add any more once I know z. Okay? And finally, similarly, p property of y given x z is again p of y given z. All of these are ways of using this single assertion, this conditional independence assertion. And you want to think of Bayes nets essentially as encoding these conditional independence assertions. Okay? And we already noticed that if in fact A is independent of B given C, then probability of A, B, C, joint probability A, B, C can be written as probability using chain rule A given B, C times B, B, C, which can be written as A given B, C times B given C times C. This part, these two pieces basically just by chain rule. Right? These two pieces by chain rule. And at this point, I realize A given B, C is nothing but A given C, because A is independent of B given C. And similarly, B given C will be B given C and then B C. So now you are able to write this as a multiplication of these distributions. Normally, for this joint distribution with 3 Boolean variables, I would need 8 minus 1 numbers to specify. But here, I'm getting by with just 5 numbers. Right? Because 1 number here, 2 numbers here, and 2 numbers here. You see what I'm saying? So everything sort of is connected. It's all connected ultimately to the conditional independence assertions. So in probability, that the main semantics come from these conditional independence assertions. Okay. Now, how do you know things are conditionally independent? This is you happen to know your domain. Do you see what I'm saying? This is you happen to know your domain. So, for example, you might know certain things are independent of certain other things. Right? So you, for example, might know that your hair color is independent of your grade in the class. Maybe not, but most of you believe that. Right? So that's your current assumption, and so you basically say that they're independent. Okay? And similarly, in general, basically, it's your domain knowledge that is giving you these conditional independence assertions. If you are trying to figure this out empirically, if you want to figure out that conditional assertions, conditional independences hold empirically, then you actually have to, for example, compute the two probabilities, probability A given B, C, and assess them. A given B, A given B, C, and A given C, and say that they're equal. So that means you would have assessed these in the wild, in the real world. Okay? Probability of A given B and C, B is true, C is true, and then you also assess probability of A given just C is true. And then those two numbers are equal, that means it must have been conditionally independent. You understand what I'm saying? Okay? But sometimes you happen to know about the domain, and so you sort of know this without having to go through all these machinations of assessing. So in general, conditional independence assertions tell you something about the domain, so the domain knowledge. Okay. Okay, now the question of course then is, why don't we just write down all the conditional independence assertions that hold in a domain? That's what domain-based network is doing, except it turns out that the number of conditional independence assertions in a domain can be exponentially large. What you really want to do is take the small subset from which everything else follows and write just that small subset. Okay? So that's basically what Bayes networks try to do. There can be exponentially many conditional independence assertions that hold in a domain, and so the brilliant idea is maybe we should just implicitly specify the conditional independence assertions by writing only the local dependencies between variables according to some topological order. Okay, and then everything else, and then they provide an algorithm that tells you, given the Bayes network configuration, whether or not a conditional independence assertion holds. You almost saw this, right? You already said, I pointed out last class that the main independence assertion that is holding in a Bayes network is a node is conditionally independent of, actually I should have said, all non-descendants given its parents. I said ancestors given its parents, but actually it's independent of all non-descendants given its parents. Non-descendants include, of course, ancestors, but also include siblings. You see what I'm saying? So that is the minimal Bayes network conditional independence assertion that holds given a Bayes network configuration. And given that, then I can answer many, many queries. I'll show you, whether or not a set A is independent of set B given set C. Okay? So that's basically what we are trying to do. Bayes network is a way of compactly representing the local conditional independence assertions. And then providing an idea called deseparation, or some people call it baseball algorithm, which sort of tells you what are the other assertions that will hold given the assertions that are already shown in the Bayes network. Okay, and let me give you more examples of this. So the simplest, as I said, actually is this, that a network, in any Bayes network, the node X is conditionally independent of all its ancestors and all its non-descendants, which includes ancestors as well as siblings, given its immediate parents. That's the main local conditional independence assertion in a Bayes network. And we use this in computing the joint distribution. Remember that. Okay? Now, the thing is, this one still leaves this guy connected to its children and children's children and so on. You see what I'm saying? Even if I give you my immediate parents, I might still be dependent, I might still be correlated with either children or children's children. I'm no longer correlated with the ancestors and the siblings. And the siblings' children, etc. But I'm still correlated with my own descendants. Okay? To expand that, actually, so this is the main conditional independence assertion. There is a different assertion, this is it's just a direct generalization of this, called the Markov blanket. And in case you forget, there is Linus with his security blanket, for those of you who remember Linux. Okay. So a Markov blanket is a blanket that a node can throw around itself to be completely secure from the influence of anybody else. Okay? And of course, the Markov blanket contains the immediate parent, but in addition, it contains its immediate children. And being the modern family, it contains the other parents of the immediate children. That's your nuclear family. Who do you call for your Thanksgiving? Your parents, hopefully, and your children, hopefully, and your children's other parents, hopefully. Right? At which point of time, then you are secure from that, evil influences of the rest of the world. That's your Thanksgiving Markov blanket. Okay? So that's the Markov blanket. And it's actually important to understand this, that in any Bayes network, once a Markov blanket is given, then the node is independent of everybody else. So if I'm trying to randomly, given a Bayes network, one of the most useful things you will do, and actually I'll talk about it a little later, is to be able to sample the value of a variable. Randomly sample the value of a variable, given some evidence. The interesting thing is sampling the value of this variable given arbitrary evidence on the network that includes the Markov blanket is the same as sampling that network given just the Markov blanket. Do you see what I'm saying? So basically it's like P A given B and C is the same as P A given B. That means giving C is not helping you. Okay? Similarly, when I am sampling a node's value, using a whole set of variables, that is a superset of the Markov blanket. All that matters is just the Markov blanket. Okay? So this is actually very useful in sampling these nodes. There is a great idea called MCMC, Markov Chain Monte Carlo, which essentially samples each node using its Markov blanket. Okay? And that's a way of actually doing inference on the Bayes network. But I'm jumping ahead. There are two ways of doing active inference on Bayes networks. One is exact algorithms that involve using the joint distribution table more efficiently. The other is approximate algorithms where you sample networks. And then, so if for example you have a whole bunch of samples, then you can then take your ratio based on just the same samples. Okay, those are the two ideas. And for large scale networks, sampling approaches are the only things that work well. And Markov chain Monte Carlo is actually a very useful approach that actually is used for sampling. That kind of comes from Markov blanket. Okay, summarizing, there are essentially two main local dependency assertions that just come out free given a Bayes network. Okay, one is this, which is a node is independent of its non-descendants given its immediate parents. This is a thing that you know. This is the minimum you need to know. And then the other is actually equivalent to another one, basically is a node is independent of everybody else given its Markov blanket. And Markov blanket is more general because here the node is not independent of its descendants. Even if you give the immediate parents. Whereas if you give the Markov blanket, it's independent of everybody. You see what I'm saying? So in that Thanksgiving party, you don't need to get the grandchildren. You can put them outside in the backyard. They won't affect you, as long as you have your children in the main table. Okay? So that's basically the Markov blanket. Okay, so these two are two things that you want to remember. The next thing, of course, is how to generalize this such that given these local Markov assumptions, if I ask any arbitrary query, given set A and set B, and then evidence set Z, or rather given a set X and set Y of random variables, and an evidence set Z of random variables, can I say X is independent of Y given Z or not? I want an actual algorithm that says yes or no. You clearly can answer some of them. So for example, in this particular case, is John Calling independent of burglary given alarm? Yes, because that just comes from the direct local independence. Okay, how about is John Calling independent of Mary Calling given alarm?
Yes.
Yes, again, because Mary Calling is a non-descendant. That also comes directly. But in general, I should be able to answer any arbitrary query of this particular kind. Okay? And to do that, we use this idea called deseparation, which is a slightly, mind-bending idea, but you need to, follow this. Okay? So here is the basic idea in deseparation. Think of this huge big network, right? Network is made up of arrows. In Bayes networks, network is made up of arrows, right? Here are the X nodes. Here are the Y nodes. Here are the evidence nodes, Z. Here are the nodes that are actually in evidence. This stuff is not in evidence. Okay, that means you know these values of these variables, but not these. The question then is, given this, is X independent of Y given Z? One arbitrary, some simple thing is actually to understand that there are paths here. between the x variables and y variables, there are arrow paths. Actually, for the purpose of doing this analysis, actually assume arrows don't have directions. Basically, any path is interesting. So any path that goes from x to y through z, you're considering that. Okay? And what we want to say essentially is, if all those paths are blocked, we'll define what blocking means. Then x is independent of y. So somehow we are trying to capture this notion of probabilistic influence flowing on these arrows. You see what I'm saying? So if every path from x to y is blocked, then x is independent of y, given z. Okay? Now it turns out there are, if you look at the actual status of the path, where it is intersecting the evidence node, the z nodes. Okay? They can only be three kinds, just at the z node. Either the arrow is coming in and going out, or the arrows are going out from z, or the arrows are coming into z. Agreed? This one we'll call it a causal path. Again, the word causal is used not in the true causation sense. It's as if we think of arrow direction as approximately causal. It's not supposed to be causal. So you call this causal path. This is called common cause. This is a causal chain path. This is a common cause path. Z is actually causing both this guy and this guy. Okay? And the third one is common effect. The thing that's actually slightly tricky about independence computation in Bayes networks is what you would like to say. The simple thing that you would have understood is, look, these two paths are blocked here. This appeals to your notions of cut sets in graphs. Like in a graph, you can have a cut set. If you remove those vertices, two other sets of vertices are actually disconnected. Do you understand what I'm saying? This is what you would really want it to be. Okay? It is actually true in a different graphical model called Markov random fields. In Markov random fields, you will have nodes like this with no directions. And basically, you will say this set is independent of this set, given an evidence which cuts them, which cuts the graph. You see what I'm saying? My point is, you would have really understood this as pretty obvious stuff if it was a cut set. It's almost a cut set, but for the explaining away part.